Okay, so this lecture is over sp hybridization. So as an example molecule, we'll look at this molecule with a triple bond, but it doesn't have to have a triple bond. It can be this molecule as well. Two double bonds on the same carbon, or it doesn't have to be carbon, it could be nitrogen. So these three molecules, so if we look at this carbon or the other carbon, the central carbon here, or this carbon or nitrogen, they only have two things attached. So in this case, two atoms. Here, two atoms. It's got that carbon and that carbon attached to it. Or two atoms in case of this carbon. And in case of nitrogen, it's got one atom and one lone pair. So two things, it's going to be sp hybridized. And so again, easy way to remember that. So if you have one S and P, so one of each of them, and if you add those two things together, the superscripts, you get two. So if you need two things attached to something, it needs to be sp hybridized. Okay, so let's go through what do the orbitals look like for this first molecule. So if we want to sketch what the orbitals look like for that, so if we went through the same analysis again, so 1s2, 2s2, and 2p2. So we're going to ignore the 1s, and we're going to promote an electron from the 2s to the 2p. And then we're going to hybridize. So since it's only sp hybridized, we're going to take the s orbital and only one of the p orbitals. It doesn't matter which one you pick because they're all three equal in energy. But to make drawing purposes easier, I find it easier to take the 2pz, 2px, undo that. I find it easier to hybridize the 2px and the 2ps and leave the y and the z alone. So we're going to take the 2s, we're going to take 2px, and we're going to hybridize. And so we're going to mix two orbitals, so we're going to get two new orbitals out. And what do those orbitals look like? Again, they're going to have a big lobe and a small lobe. So two electrons went in, two electrons went out, came out, two orbitals went in, two new orbitals came out. So now we're going to arrange two orbitals on carbon to maximize the distance between them. So how would you arrange two things to maximize the distance between them? You would put them 180 degrees apart from each other. You would put them linear. So if we take carbon with one of its sp going towards the right, and then its other sp going towards the left, so big lobe towards the left, small lobe towards the right on the back side of the nucleus. And then both carbons are the same, of course. So the other carbon is going to have identical set of orbitals, just a mirror image of it, of the first one. So that would be both carbons sp hybridized orbitals. And then each carbon, of course, has two unhybridized orbitals. So we still have 2py, 2pz, and each carbon's got two sp hybrids, so we still have four orbitals go in, and we still have four orbitals. It's just that now two of them are hybrids and two of them are not. So if we sketch py and pz, so each carbon's got a py orbital that's not hybridized, and then each carbon's got PZ. And if you remember, PZ would be in and out of the plane. So one lobe goes behind the paper and one lobe comes in front of the paper. And then each of these has one electron. Each of these has one electron. And then each sp orbital has one electron. Right? And you can see that in this diagram. Right? Each carbon's sp has one electron, and each py and pz from each carbon has one electron. And then what's left is we got to draw all the hydrogen atoms. And each hydrogen brings one electron. So we still have what? 2, 4, 6, 8, 10 electrons in the molecule. And so the two PYs overlap side to side, so that would make a pi bond. And the two PZs overlap side to side, so we can try to indicate it like that. So that would make another pi bond. And the bond between the two carbons with the sp overlapping the sp would be a sigma bond. And then this would be a sigma bond as well, sp overlapping s. And this would be a sigma bond, sp from carbon overlapping hydrogen's s. Okay, so in this structure, so two of these lines, so one of these lines is representing the sigma bond, and then two of these lines are representing the two pi bonds. So anytime you have a triple bond, one of them is always sigma, two of them is always pi. So if we were to sketch the bonding in that molecule instead, well, the only difference is there's a lone pair here, so you would not have a hydrogen atom there, you would just have a lone pair of electrons sitting in that sp hybridized orbital. So it would basically look like there would just be a lone pair in that sp hybridized orbital. And so then the bonding will, of course, in the molecule is from hydrogen to carbon and nitrogen, 180 degrees, or in this molecule from hydrogen to carbon is 180 degree bond angle. So anything that's sp hybridized will have two sp hybrids 180 degrees apart and two p orbitals that are mutually perpendicular to each other. So if it's sp hybridized, right, then the orbitals look like that. So we got py overlapping py, pz overlapping pz, front and back, and top and bottom overlap counts for one bond. And then this will be an sp going to hydrogen's s orbital. This will be an sp hybridized orbital going to hydrogen's s orbital. And the line between the two atoms will be an sp overlapping with a sp from the other atom.